In southern France, there's a bridge that seems to float above the clouds. At its highest point, the Millau Viaduct reaches 343 meters into the sky. That makes its tallest mast higher than the Eiffel Tower. But its height isn't even the most impressive part. So how do you actually build something like this? Before the bridge existed, traveling through this part of southern France meant dealing with a major bottleneck around the town of Millau. The A75 motorway connects central France toward the Mediterranean, but there was one enormous obstacle in its path: the Tarn Valley. Taking the motorway directly across the valley required a bridge on an extraordinary scale. Not just long, not just tall, but strong enough to carry motorway traffic while remaining stable hundreds of meters above the valley below. Eventually, engineers settled on an ambitious solution: a multi-span cable-stayed bridge. The finished Millau Viaduct stretches approximately 2,460 meters from one side of the valley to the other. Supporting it are 7 enormous concrete piers. And this is where the scale becomes difficult to comprehend. The tallest pier, known as P2, rises approximately 245 meters from its foundation to the bridge deck. Add the steel mast above the deck, and the structure reaches roughly 343 meters. For comparison, the Eiffel Tower is around 330 meters tall, including its antenna. And yet, these enormous piers had to support a remarkably slender roadway. That was intentional. A massive, bulky bridge could have dominated the landscape. Instead, architect Norman Foster and engineer Michel Virloge helped develop a structure designed to appear almost weightless. But designing it was only half the challenge. Someone still had to build it. Construction began in 2001. The first major challenge was creating the foundations. Each pier would transfer enormous forces into the ground, so engineers constructed deep foundations beneath them. From those foundations, the concrete piers began rising. But these weren't ordinary rectangular columns. The piers gradually change shape as they rise, eventually splitting near their tops, helping provide the required structural behavior while giving the bridge its distinctive appearance. Special climbing formwork allowed crews to repeatedly pour sections of reinforced concrete higher and higher. Eventually, 7 enormous supports stood across the valley. But there was still a problem. The roadway wasn't there, and building it piece by piece hundreds of meters above the ground wasn't the preferred solution, so engineers did something much more interesting. Rather than assembling the entire steel deck over the valley, huge sections were constructed from both sides. Then, they pushed them out over the void. This technique is known as incremental launching. Hydraulic equipment gradually moved the enormous steel deck forward, meter by meter, pier by pier. But there's an obvious problem. Imagine holding a ruler over the edge of a table. The further you push it out, the greater the unsupported length becomes. Now imagine doing that with a steel motorway deck weighing tens of thousands of tons. To control this, engineers used temporary supports and a launching nose at the front of the advancing deck, helping it reach the next support. The two halves continued moving toward each other from opposite sides of the valley, until finally, they met. The gap was closed with remarkable precision. The motorway now stretched across the Tarn Valley, but the bridge still wasn't finished. Above the roadway sit 7 steel masts, each rising about 87 meters above the deck. From these masts extend the cables that give the Millau Viaduct its unmistakable appearance. But the cables aren't decorative. They're fundamental to how the bridge works. Traffic pushes downward on the deck. The stay cables carry forces toward the masts. Those forces travel through the structure and ultimately down through the piers and foundations into the ground. In simplified terms, deck to cables, to masts and piers, to foundations to ground. It's an enormous system for controlling and transferring forces. And because the bridge deck is so high above the valley, engineers had another invisible force to worry about: wind. At this height, Strong winds can place significant loads on a bridge, and long, slender structures can behave in unexpected ways when exposed to aerodynamic forces. Engineers therefore tested the bridge's shape extensively, including aerodynamic studies of the deck. Its streamlined cross-section helps airflow around the structure rather than creating excessive aerodynamic instability. The bridge was designed for extreme wind conditions far beyond what drivers would normally experience. So, although Millau looks incredibly thin, there's an enormous amount of engineering hidden inside that elegance. After roughly 3 years of construction, the Millau Viaduct was inaugurated in December 2004. For Norman Foster, seeing the finished structure for the first time was overwhelming. He later admitted he was almost physically sick with anxiety, waiting to see if years of calculations had actually worked. They had. The project had transformed an enormous geographical obstacle into what looks like a simple line across the landscape. 7 piers, 7 masts, a steel roadway stretching almost 2.5 kilometers, all suspended hundreds of meters above the valley, high enough that on certain mornings, the bridge rises straight through the clouds, as if the road simply floats above the valley entirely. But perhaps the most impressive thing about Millau isn't any individual number. It's how little of that complexity you actually notice. From a distance, the bridge looks almost effortless. And that's often the strange thing about great engineering. The more complicated the problem, the simpler the finished solution can appear. The Millau Viaduct isn't remarkable simply because it's tall. It's remarkable because engineers had to solve problems involving geology, structural forces, wind, construction logistics, and enormous scale, and combine those solutions into one incredibly slender structure. A bridge that doesn't just cross the landscape, it almost disappears into it. And that's what lies beyond concrete.
If you enjoyed seeing how engineering makes structures like this possible, subscribe to Beyond Concrete.